Now we're going to look at the position vectors. This is the slender bar body, the rigid body, and we're going to define the origin at point A. And when we assign the origin, we're going to assign it as O as well, right? So we're going to obtain the position vector of A, and then uh, the mass center as well as the B at the end D. Now the position vector for origin is given by 0I plus 0J, because we are using the Cartesian coordinate system. And then for that reason we have position vector of A. This one will be equal to position vector of O I plus 0J. Next, we're going to evaluate the position vector of G. And we will be using the kinematic relationship. So G, the absolute values is equal to the absolute position vector for point A and A plus the position vectors, relative position vectors of point G relative to A. And if we look at the problem that we're going to solve, we requires to evaluate the angular acceleration, and for the kinematics of the body, rigid body, we also want to evaluate the uh, angular speed, right? So we want to convert the velocity, the position vector in equipolar coordinate system into the Cartesian coordinate system for point G. So what we're going to have here is R G slash O, which is can be written in matrix, right? So we're going to write it in matrix. So we have X, Y in at G. This one will be equal to 0 in X direction, in Y direction for uh, point A. And then we have the conversion matrix for point G relative to A. So I'm going to remove here this part, and this is a position A, right? And this one is R, and this is the X, this Y, and if you are evaluating based on equipolar coordinate, the angle is measured from the horizontal line to that point, and since the angle here is 30°, right, and on this side is 60°, so the angle that is made here will be 180 plus 60°, which equals 240°. So we have cos 240 sine 240 minus sine 240. So I need to write again because this bit is too small for me. So we have x and y for g. This one is equal to 0, 0 for point A plus cos 240 sine 240 minus sine 240 cos 240, and then the distance is 2 feet uh, between the T and A. So I'm going to use the Symbol Lab metric calculators. So I share with you the website here. So I just use the matrix 2 by 2. Right, we have cos 250, 240, sorry, cos 240. We have cos 240 sine 240 minus sine 240, and we have cos 240, and then we're going to multiply this with the 2 by 1 matrix. Let me see. We don't have that 2 by 1 matrix, yes. And then we have 2 times 0, and then we can do the calculation. The software is calculating. So these are values that we get. We have minus 1 and minus square root of 3. So we have this one equal to, because this one is 0, we have minus 1 and square root of 3. Uh, um, RGO is minus 1.0 I plus minus square root 3 J. Now we're going to look at the position vector for B. Position vector of B is R B. The absolute position will be position vector of RG point plus the position vector, relative position vector of B relative to G. Right? So we are using the same setup just now. So we have this is a coordinate system that we define at G. So this one is X and this is 1, and we have B there, and the angle is measured from that direction. We have 240 degree, right? And this one is also 2 feet. So when we evaluate the RBO, the absolute values evaluated at B, this one is equal to minus 1 and minus 3, and we are using this cos 240 sine 240 minus sine 240. Let's just use theta here, I think. Sine theta minus sine theta cos theta, and this could give a 2 and 0. So we're going to have, after we put in the value of 240 here, we're going to have the value of -1 and square root 3, right? So we have for here we have -2 and 2 power of 3, and we can write the equation for position vectors. Here is 2i minus 2 square root of 3j. So there is a position vector uh, for b, and we can write again for the whole point of interest, right? We have O is 1 is 0i plus 0j, and then we have A is also 0i plus 0j, and Rg absolute values is minus 1.0i minus square root 3j, and for B the absolute values will be minus 2i minus 2 square root 3j.